Assalamu alaikum. Yes. So lesson today is multiplication rule. And it's really the main rule in chapter 4 in probability theory. So what is the multiplication rule and where did it come from? Do you remember the last example when we had a two-way classification table like that one, where people are classified two different ways, maybe based on gender and then based on their opinion? So we had, for example, male, female. We also had some people who are against and some people who are in favor. So let's put any numbers, like maybe 3, 7 here, 4 here, 6 here. So there was 4 types of questions I usually ask in this case, and the questions that are common are: the first is simple probability. So I select one person from this group. What is the probability that this person is a male? What is the probability of getting a male? How many males are there? 7, yes. 7 out of how many? 20. Right, so the probability of this event, simple probability, is 7 over 20. The second type of questions was finding the probability of two events that happen at the same time, the joint, the AND probability. Find the probability the person is male and against. So the probability that the person is male and against, there are 3 people like that, yes. And of course, you're selecting from the whole company or the whole group of people, so that will be 3 out of the total 20. Okay, so these are the 2 easy questions. Let's look at the 2 confusing questions for many students. Find the probability that the person selected is male or against. Male or against. See, the or means the union. So you not get all the male, which is 7, as you said. And the against are those people, right? So you just make them united. So it will be 4 and 3 and 7, which is 14 over 20. Okay, so that's the union. The or is the union, is to just add them all together, but don't add anything twice. Yeah. Yeah.
3 over 7.
Yeah, no, against and male is the same as male and against. Still 3 over 20. M and A and M, same, because it just means happening at the same time. Okay? Any other questions so far?
Yes.
Because it just came in. I'm just reviewing what happened last class. Okay? So I had 4 types. I said you have simple probability, you have joint probability, which is and, I have the or probability, which is the union, and finally I have the given or the conditional probability to find the probability that the person selected is male, given he is against. Find the probability of male given against. Given against, which means I have a piece of information I'm giving you, which is, by the way, he is against. I know he is against. So from those who are against, what is the probability that he is male? So it's like male from against. How many are against? 10. So that's the only case when you divide by 10, not the total number. When you have a conditional probability, we don't divide by everything, we just divide by those who are given, which is, in this case, those who are against. Okay? And then, how many from those who are against are male? Because I'm asking find the probability of male, right? There are 3 of them, so that would be 3 over 10. Does it make sense? So I have 3 men out of all of the people that are against, which is 10, 3 out of 10.
Probability of against.
Yeah, it's not the same if you switch that probability of against the given male. It's not the same, because now given male means you know he is male, and you divide by the total number of male, which is 7 in this case.
Yes.
And from those also there are 3 against, right? Okay, so they're not the same, because you divide by the number of outcomes in the given event. You divide by the number of outcomes in the given event. So if you're given male, you divide by the number of males. If you're given against, you divide by the number of those who are against. That's the only case when you divide by something else. Sorry? Because given male, you divide by the number of people who are male. Here given against, so you divide by the number of people who are against. All the male, yeah. Now, given male means I know he's male. So it's like selecting from the male. Okay? Okay? So that was a revision of the last class probabilities. That's not the multiplication rule yet. We were just reviewing what we did last class. Okay? No. This is not yet. This is not the multiplication rule. This is a two-way classification table that we had last class. Okay? But I am trying to tell you that this two-way classification table can actually be converted to a tree diagram. It can be converted to a tree diagram. So let's convert this into a tree diagram. So I'm going to just erase some of these because I need the space. Okay, so if you convert two-way classification table into tree diagram, you have two stages because you have two ways of classification. You have the gender and you have the opinion. So the gender will be a stage and the opinion will be a stage. It doesn't matter which one you start with, but you have a stage for each way of classification. So if you start by gender first, the person selected can be male or female, and after that, the person, whether male or female, they can have an opinion which is against, or they can have an opinion which is in favor. The same thing here, against and in favor. So at the end, you have a person who is, who is male and against, male and in favor, female against, or female in favor. Okay? In favor. Okay, let's put the probabilities on the tree diagram. When you select one person, what is the chance that the person is male? Find the probability of male. Yes, not half. Is it half, really? Not half. It can be male or female. We just got that. It's here. Come on. The probability of male is 7 over 20. 7 over 20, because we have the number of males are less than the number of females. So the chance of getting male is less. Right? It's not 50-50. If they are 10 male and 10 female, it would be half-half. From the diagram, I have two outcomes. But it doesn't mean that the probability has to be the same. It could be different probability.
So how can you calculate the probability of the fraction without the table, just the tree?
No. We're getting the tree diagram from the table, in fact. Because all the information is given in the table. I'm just converting the table into tree diagram. So everything is coming from the table. All the probabilities will be coming from the table. Okay? So the probability of male, according to the table, is 7 over 20. Right. The probability of female, according to the table, 13 over 20. And you notice when you add them, you get 1. You get 1. And that's always the case. Whenever you do branching, you have to have the sum always 1. Okay. Now, suppose you got a male. What is the probability that this male is against? So that means what? That means given male. What is the probability this guy is against? That's the probability of against given male. So from the male, which are 7, yes, how many of them are against? That's 3, that's 3%. So you notice here that the first stage, you have the simple probability. But starting from the second stage, you have conditional probabilities. Because something happened already before, and you're building on that. So you always have a probability of something after something else happened. So given something else happened. You understand? So that's why everything will be conditional. Like this probability here, this is the probability of I given.
Given female?
No, here. I given male, right? And here it would be the probability of A against given female, and so on. Okay? So all the second stage, this stage here, this will be all given probability or conditional probability. The and is the outcome. This is female and against. This is the one you're talking about. This is now, both happened. This is and. Right? So this is and. The joint probability is the outcome of the probability experiment. But now we're still doing the second stage, which is conditional. Yeah.
So would it differ if it's like probability of against given male or male given against?
Yeah, there's difference, but we already choose to start by gender first and then the opinion. If you want the other, I have to switch to the tree diagram. Yeah, everything will be different, yes. Usually. Okay? Usually that's the case, and sometimes not, so, but usually it's the case. This will come later. But I'm telling you for now, to convert the table to tree diagram, you have the choice. As long as in real life, we didn't have one happen first and then the second, because we didn't select the gender first and then the opinion. We just select randomly. So these two steps of analysis are actually just logical steps. That's your way of analyzing the problem or the options. And your way of analyzing could be different in another one. It's not real life steps. It's not like you toss a coin and then you roll a die next. It's not like that, right? So if it's just these two stages are one thing happened, which is one guy selected. So in this case, you have the choice to choose the order. So we just choose gender first. So let's just continue the tree diagrams, build it. Now, how do I write this probability of I given m? I given m. I given m. 4 over 7. 4 over 7. So from the m, which is total 7, I is the probability of I. Okay, the probability of A, probability of just delete it. Okay, A given F. Yeah, just A given F. From the female, how many are against? 7 over 13. And from the female, how many are in favor? From the female, how many in favor? They are 6 over 13, and as I told you, when you add these two, you also get 1.
I given m with 4 over 10.
No, 4 over 7, because given m, which means select from the m, which is 7 people. Given, no. I given m, and this is all the m. Given m. Given m means you divide the number of male. You write all the numbers, then you get all the conditional probabilities of the tree diagram. That's what we just got all the probabilities. See these two numbers, when you add them, you get 1, right? This one and this one, and also if you add these two numbers, because every branching you get different probabilities. Then, but when you add them, it should be 1. Okay. Okay. So what we are doing now is just try to match, the probabilities, in the tree diagram with the probabilities that are actually in the table. We'll see how we can convert the table to tree diagram. Okay, this is just, by the way, it's just an exercise. Usually I don't give you a table and you have to do a tree diagram. But sometimes I give you a question as words, sentences. And some people choose to implement these sentences in table, like what happened last class. You remember question number 5? And some other people choose to do it as a tree diagram. In fact, if the numbers are given like this frequency, 3, 4, 7, 6, all these as given numbers, then the table will be easier. But if percentages are given, okay, as we will see other examples, then the tree diagram will be easier. But anyway, I have another purpose. Why am I doing this? I'm trying to discover with you the multiplication rule. I'm doing all of this to discover the multiplication rule. Now, how about the outcomes? Find the probability of m and a. We already have this also from the table. What's the probability of m and a? Let's do that a different color. M and a, yeah, we just got that. That was 3 over 20. Find the probability of m and I. M and I is 4 over 20. See, sometimes we don't write the and. So mi is the same as m and I, right? Okay, f and a both happen at the same time, f and a, that would be 7 over 20. And then fi, that's 6 over 20. And of course, when you add them all, what do you expect? They have to be 1. When you add them all, they have to be 1. Otherwise, you have a mistake somewhere. Any probability experiment, when you add the outcomes at the end, you must have 1. The outcome probability, when you add them, you get 1. Now we finished the tree diagram. We probably learned something. We learned what? We learned that the first stage, simple probability. The second stage is conditional probability. Actually, if there was more stages, suppose you have 3, 4, 5 stages, every one of them would be also conditional. So given what happened before. And the outcome at the end is actually the joint probability. These are the joint probabilities. So this is always simple. Okay, this is conditional. maybe more, maybe if I have more stages, it will be all of them conditional, but the last one will be the joint probability, which is the AND probability. This is a structure for tree diagram, always like that. It's always, any tree diagram is like that. Start simple, after that conditional, finally you have the joint or the AND probability. Now let's look at the discovery here. Look at this discovery. Have you seen Discovery Channel before?
Yes.
See, that's like Discovery Channel. What is the probability here? 3/20. Okay, where did you get that from? We got it from the table, because we know everything got from the table, right? But you know what? I could have also got this from the tree diagram. How come? Look at the probability here, 7/20, 3/7. If you multiply them, what do you get? 3/20, which is this number, the outcome, right? Is this just by chance happening? Is it just coming by coincidence? Just multiply this number and this number, and give you 3/20. Yeah, if you know how to multiply fractions. Do you know how to multiply fractions?
So it's the probability of a normal class and
The probability.
the probability of a given.
Yes, it's the probability of the first event that happened first, and then the probability of the second happened given the first. So this branch already, how do you get this outcome? It's coming from the first step here and second step here. So this branch is here that takes to this outcome, has probabilities. If you multiply them, it will give you the outcome probability. And this is exactly what the multiplication rule is. The multiplication rule is that to get any outcome of this, just multiply. We just discovered that. Not only here, look at the second outcome. 7/20, if you multiply it by 4/7, you get 4/20. And all of them are like that. So that's always the case. That's always the case. That's how the multiplication rule is this probably discovered. So you have just any outcomes that happen at the end of that tree diagram. How do you get the probability? Simply multiply all the probabilities on all of the branches that lead to this outcome. 2 stages, 3 stages, 4 stages, 5 stages, whatever it is. So let's just write this discovery here with a formula. Let's take the example that we just found. So I'm saying that the probability of M and A is what? Probability of? No, not the number. Yeah, the probability of M times A given M. So the probability of the first and second together means happening at the same time, because what happened here, I have both male and against at the same time. So this and this happen at the same time is the probability of the first times the probability of the second given the first, not just the second, because the second happened conditionally after the first. So in general, if I want to say, find the probability that I have X and Y, what would be the probability? Probability of X, yes, because it happened first, assumingly, times the probability of Y given X, the second given the first. Okay? So that's called the multiplication rule. The first, and then the second given the first, which is the conditional probability. So now let's come up with a general way of looking at this multiplication rule. I may not just have 2 outcomes, I may have 3 or more outcomes. Suppose the probabilities of these, 3 or more sequence of events. I have sequence of events, one happen after another. Maybe in real life happening one after another. Maybe just a sequence in which you choose to analyze the problem. So if I have the probability here 0.3, here 0.4, here 0.7, at the end what I have A, B, C, which means all of them happened at the same time. Yeah, so to get this probability is simply to multiply all of these probabilities on the branch that lead to this outcome. So it's 0.3 times 0.4 times 0.7. So you're just multiplying. This is what's called multiplication rule. Yeah.
This probability of A multiplied by
Yes, exactly. This is the probability of A. Yes.
multiplied by probability of B given
Very good. This is B given A. Exactly. Perfect.
C given B.
And this is, I'm just going to do that. This is the probability of C given B. If B only happen in one time, but if B happen again in different part of the tree diagram, it is safer to just say AB, because what actually happened at this point is both A followed by B, right? So you can write B, but it's better to write AB because maybe there's another place will B appear. Okay? So, but the main point is that it's always after that conditional property. So this is conditional property. This is conditional property. But here, this is simple probability. And everything after that becomes conditional until you reach the outcome at the end. And the outcome is a joint probability of all of the sequence happened. A happened, B happened, and also C happened. So this is the main idea of the multiplication rule. Yes?
I didn't get the probability A, B,
These are just theoretical examples. This is not, A doesn't have to be something. Just A is anything, something happened, and then B happened after that, and then C happened. Suppose A is the probability of rain. The probability it will rain today is 0.3. And B is the probability that you will get the full mark in the quiz. And then C is the probability that you will go to the movie tonight. So what is the probability all of them will happen at the same time? You just multiply them. Because at the end of the day, you went to the movie, you got a full mark, and it was raining.
Yeah, but do you think that you wrote conditional and simple?
Yeah, because this is, because in general, the examples I just said are just some of the examples, which probably don't depend on each other. But in general, this B depend on A. So the probability of B given A happened, maybe the probability that you get the full mark if it's raining is different from the probability if getting the full mark if it's not raining. Maybe you don't like the rain, for example, so it affects you somehow. Or maybe it's the opposite. So in general, B happened after A, probably it depends. So we say B given A, because that's not any B, that's B given A. All right? C depends on also what happened before.
But B doesn't depend on anything.
B does,
depends on A and A doesn't depend on anything.
Yes, A does not depend on anything, exactly. Because this is what happened first. At least this is the way if your choice of the analysis of the problem. Okay? We'll see other examples of dependency and independency, but this is the general rule of the multiplication rule. Maybe I start with easy examples first, because maybe the way looks complicated when it's very theoretical. Let's just have a simple practical example, which is tossing a coin. When you toss a coin, what happens? You get head or tail. What is the probability of head? Half. What's the probability of tail? Also half, right? Okay, so we call this the probability of head, and we call this the probability of tail. Suppose you want to toss the coin one more time. So if you got head the first time, the second time can still be head or tail. What is the probability you get head on the second time? Half. But this half actually is the probability of getting a head given H, exactly. Given H, because that's a head on the second toss, given the first is also head. It is possible that you get head given the first is tail. But in this case, the probability is also, it's also half. It didn't change. Right? So that would be the probability of head given tail. Same thing here. This would be half, which is tail given head. And this will be tail given tail. Yeah, that's the probability of tail given tail. So at least now you know the names, and the probability everywhere is going to be half in this example. Now if you ask me what is the probability that all are heads? You toss the coin only twice. Suppose toss the coin twice. Toss coin twice. What is the probability that all of them are heads? Which means head. That means the probability of head. In this case, this outcome here, which is head, is half multiplied by half. So this will be half times half, which is 1/4 or 0.25. Okay? So that's a simple example of using the multiplication rule. You have a sequence, which is tossing a coin, getting a head. Another event, you're tossing a coin and getting a head. What is the chance you got head on both of them? Is simply the multiplication of the first event probability and the second event probability. Yes? No. What? Add what? How many heads you?
All same line over how many lines you have?
Oh, you talk about the outcomes, like I have head here and head tail after that, and then tail head and tail tail. Is that what you're talking about? And you're saying all of them are equal, and that's why, because all of them are equal and the sum is 1, so each one is 1/4. Yeah, in this case, yes, because you have equal probability everywhere. Like head and tail is always half-half. But in some other examples, it may not be like that. So yes, you are right. You can make use of being everything equal, but not every example will be like that. So in general, if you want outcome probability, when you use the multiplication rule, just multiply it like that as a sequence of events. Okay? Let's see another example like that. You know, the example of boy and girl is the same thing. So suppose a family has 4 children. Okay, assuming the probability of boy and girl is the same, so find the probability of getting 3 boys followed by a girl. So again, assume boys and girls. How do you write girls? Of equal probability. Draw the branch steps that will take you to this outcome. So the first born child could be boy or girl, right? Here he's interested in being a boy. The next child, boy. The next child, boy. And then the next child, girl. So that's what he's interested. He's interested in the probability of boy, 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 and then girl. So step by step, the probability of getting boy in the beginning is half. The probability of getting boy after that is half, and then half. How about the girl? See, the boy is also half, but the girl is also half. Which one I want? In fact, it doesn't matter. I want the girl, right? So this is the branch that will lead to this outcome: boy, 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 girl. So the probability in this case would be what? This is what? 0.5. Okay, so it will be half to the power of 4. Just multiply 0.5 or half multiplied by itself 4 times, which is 1/16. 1/16.
So in the end, why do you have two branches?
No, I always have 2 branches, but I didn't graph everything. See, I always have boy or girl, and then I have here also boy or girl. See, I didn't do the whole tree diagram. I'm just doing part of it. Okay, I just need this part that give you boy, 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 girl. Okay, so don't draw the tree diagram all the time. Just draw the part that you need based on the question. Don't waste your time drawing the whole tree diagram. Sometimes it's very complicated, and you really don't need it. Okay, so the example of boy girl very much looks like the example of head and tail. Okay, you see another example? Suppose you roll a die twice. Roll a die twice. Roll a die. There are many examples. That's the problem with this rule. There's just so many examples I can have for this rule. And that's opened the door wide for, problems, examples, exercises, questions, many things out like that. Roll a die twice. Find the probability of getting 2 4s. 2 4s. Yes, exactly. Whatever is 6. Because the first time can get a 4 or not 4, right? Second time can get also 4 or not. So if you want 4, that's 1/6. That's 1/6. So the probability will be 1/36. Clear? Okay. The first time you get a 4 when you roll a die, what's the probability? 1/6, because you can get 1 or 2. See, the die has 1 or 2 or 3 or 4 or 5 or 6, right? We're interested in the 4. What is the probability of getting a 4? 1/6. Now, roll the die again. Got it? Okay. Any other questions? How about find the probability? Let's do that in a different color. Find the probability of getting 2 even numbers. 2 even numbers. Would be what?
3 over 6.
3 over 6, that's the first one being even.
Multiply with 3.
Multiplied by 3 over 6 also, yeah. So an even number is half. If you multiply it by half again, so that will be 1 over 4. So the first number is even, that's half. Second number is also even, that's another half. You multiply them. You understand what's happening? Yeah. Okay, let's do the tree diagram. It helps. The first number can be even or odd. The even, how many numbers are there? 2 or 4 or 6. That's 3 possibilities. 3 out of how many? 6 possibilities. So that's 3 over 6, which is half. Okay, and then another one even will be another half. Am I too fast? There are just too many examples. There are just too many examples. I'm trying to cover as much as I can in the class.
You want to leave the numbers from the die, right?
Yeah, you're rolling the die twice anyway.
Yeah, so it's the same question.
Yeah, same question. I didn't change the question. I was just giving it like this is question number A. It's question number B. Okay, or maybe A should be here. Find the probability of getting 2 4s and then getting 2 even numbers. All right. So that's an example about the die. What else? We can have questions, because I just wanted to show an example that the probability is not always equal. So that would be 1 over 6, sometimes 1 over 2, sometimes 1 over 3. Suppose you have a quiz out of 5 questions. Okay? Multiple choice. Each question has 3 choices. Okay? Each question has 3 choices. Okay, and the guy comes to the exam not ready. He doesn't know the answer to any one of them. So he randomly just selects anything. Okay, what is the probability he will get all of them correct? All of them right. Get the full mark.
1 over 3, 3 over 5, 1 over 3.
1 over
3.
1 by 1. What?
3 over 5 multiply.
1 over 5? Why 1 over 5?
So 3 choices.
3 choices becomes 1 over 5? Or 1 over 3? You have 3 choices, just like A, B, C, and you don't know the answer. Maybe some of them right, some of them are wrong. Only one is right, right? And you're choosing randomly. What is the chance that you will choose the right answer? 1 over 3. And the wrong will be 2 over? Yes, 1 over 3 power 5. So the chance you get all of them right, that will be actually 5 times. So the answer will be 1 over 3 power. That's it. The chance you get the first answer right is 1 over 3. Second answer right, or second question right, 1 over 3. Third, 1 over 3. All of them right. This is like first and second and third among the and. This is a joint probability. This is the outcome probability. So this will be just multiplication rule again. Just multiply them all. 1 over 3 here, 1 over 3 here, 1 over 3 here, and so on. Okay. So this is some of the questions. Huh? Yes. I'll upload this in Blackboard. Don't worry about it. Inshallah. Okay, now I want to give you an example of multiple selections, because multiple selections is one of the very famous examples here. So I start by selecting from a large population. Like suppose I know that 15% of students smoke in general. Okay, so if I select 4 students, what is the probability that all of them smoke?
Over 0.15?
No. See, do it step by step. Do the tree diagram, graph the tree. Learn to do this. If you draw the tree diagram correctly, then the problem will be easy. Just ask yourself, the first one selected, what is your options? What's your chances? Smoke or don't smoke. So the first guy could be smoker or non-smoker. What is the chance he will be a smoker? 15%, which is 15 over? 15 over what? 100. 15% is 15 over 100, which is 0.15. The chance he's non-smoker will be, yeah, 85%, right? So the next guy smoker, what's the probability? Still 15, 1.15 smoker, and so on. Okay, now I got it. All of them before will be, yeah, power 4, 15 power 4. Okay, so simply you take the first one chance of being smoker, which is 15%, which is 0.15, and then multiply this 0.15 by itself 4 times, which means power 4. Okay, now, so that's one of the common questions. Also in this part, we have a percentage of the population that some of them do something, the others don't do it. And I want all of them, for example, after being selected to be from those who do it, or the opposite. Find the probability that all of them don't smoke. Find the probability that all, or none of them smoke. None. How do you write none? N-O-N-E, right? None smoke. Okay, none of them smoke. So in this case, the others, which will be 0.85 to the power of 4. That's the probability that no one is actually smoking. Okay, so this is some of the questions of the multiple selection, selecting 4 or 5 or 6. Are you tired? Okay. Is this only one type of questions that can be asked, like find the probability all of them or none of them? In fact, there are other types of questions. So let's start looking at what could be the variety of questions where I can actually use the multiplication rule. So far, the questions have been basic. Just use the multiplication rule one time, and that was it, right? Actually, this is not just about the multiplication rule. It actually has a lot of uses. So let's look at this example. I have a container with 3 red balls and 2 blue balls. Okay? And then I'm going to select 2 balls. I'm going to ask you, what is the probability of getting 2 blue balls? Don't rush. You always rush in the answer. See, this part should not rush. Should always do a tree diagram, and should always consider step by step. Consider this, we have multiple stages. You're selecting one. If you're selecting 1, 2 over 5. You said 2 over 5. You are right. 2 over 5, but that's only for the first ball. So the first ball to be blue is 2 over 5. To be red, the probability is 3 over 5. Now the second ball, if you select it, still can be blue or red. So what is the probability the second is blue, given the first is blue? 2 over 5 also? Are you sure 2 over 5? 1 over 4. Someone saying 1 over 4. Yes, it depends, exactly. It depends if you took the ball and did you put it back or did you keep it? So that gave us 2 options to think now. Okay, so when you select from a large population, it doesn't matter. Like the previous example, when you're selecting a student from so many, it didn't matter. Because big population doesn't affect much, when you take 1 or 2 or 3 or even 10. But if you select only from 5 or 50 or any number that you know, then taking 1 will change the distribution of colors, right? So in this case, a very important question you have to ask yourself. After the guy selected the ball, did he put it back or not? Usually, if you take something, do you put it back? Usually not. If you take something, you actually want to use it, you want to buy it, something like that. But it's sometimes given, sometimes not given. So if I say with replacement, it means replace, which means you put it back. That means you put it back. Okay? But if I say without replacement, which means you keep it. And usually this is not mentioned. You know why? Because that's usually the case. Usually when you take something, you don't put it back. So this is the question. Didn't mention anything at all. So if it didn't mention anything at all, it means you actually took it. Because that's usually normally what happens in life. You buy a marker, you take it, you keep it, you go to the counter and you pay for it. Okay, so the probability according to this example of blue given blue will be 1 over 4. Because you took 1 from the 5, so the remaining is 4. And the probability of red given blue You took the blue already, right? That's 3 over 4. And of course, when you add them, you get 1, and that's important to remember. Okay? So if you said 2 blue, خلاص, that's enough. I don't need to continue the tree diagram. 2 blue means blue, blue, right? And the blue, blue means 2 over 5 times 1 over 4. So I use a multiplication rule to get this outcome, which will be 1 over 10. Okay? Clear that? Any question about that?
The 1 over 4 is for what?
1 over, this is a 2 over 5 probability of blue, and this is 1 over 4, which is blue given blue. But remember the outcome here is BB, right? So it will come from where this outcome? From this branch, right? So we just multiply the probabilities of this branch that lead to this outcome. Right? This is the multiplication rule. Remember, what's the lesson today? Still in the multiplication rule. Okay? So we just multiply the probabilities on the branch that lead to this outcome.
How is the blue given blue 1 over 4?
Because given blue means you took blue, so just hide this blue for a second.
You took 1.
I took 1, so just hide it.
Yeah.
So remaining 1
Over 3.
out of the total, which is 4.
Yeah.
Which you're selecting now from 4. If you take 1,
But given.
now given blue means blue is taken. I'll just take it out.
Yeah.
So now you're selecting again, second time.
Didn't we say when you say given something, you just choose that population, not the whole population?
No. That was in the have frequency table. Now we're looking at the concept of given. Given means something already happened. What happened here? I already took the ball. So the distribution of curve change. Given is a piece of information. In general, the word given means I am telling you something happened. That's a piece of information. That's its original meaning. So what is the piece of information? The ball, first ball selected is blue.
Yeah, the first one, when you say given, you choose that only.
That was when you had the frequency table. That was when you had a two-way classification table. Now we're moving to tree diagrams. Okay? So when given male or given female, which means I'm telling you he's male, so it's like selecting from the male. That was in the table. Now we have tree diagram. I'm telling you selecting from the whole container. I'm saying given, but it's still totally different because when you have two-way classification, the 2 steps of the tree diagram was only 1 selection. Now the 2 steps are actually 2 selections. So it's totally different example. Yeah. If we replace it, then there will be still 2 over 5. This will be 2 over 5 also. If we say with replacement, and suppose I say here with replacement, then this will become 2 over 5. Okay, but I didn't say that. So, okay, and anyway, I just put the ball back. So we took the ball, so 1 over 4, and then the probability of red is 3 over 4 because it will be 3 red and. Okay, now clear? So this question, we just answered the question. Probability 2 of them blue. How about let's do another one. Find the probability 2 of them. Find the probability that 2 of them are red. Yeah, it's just exercise for you. Why don't you try that? Just continue the tree diagram and try to get the red. Yes. Yes, very good. Yeah. Just continue the tree diagram. Try to fill the tree diagram, the missing part, if you understand what happened. I'll give you what, 5 minutes? 3 minutes? Do you have a paper? Do you have a paper or pen? Try to graph this tree diagram. Start graphing because we need to start. Be active. Try to continue the tree diagram. Please continue the tree diagram. Just fill it all with all possible outcomes. And get the probability that both of them are red. Yes, what's the answer?
3 out of 10.
3 out of 10. Okay, so the second time you select, it can still be blue or red. Given the first one red, the total number of red becomes less, become only 2 remaining, and the total becomes 4. So you have, in fact, 2 over 4 here, and you also have 2 over 4 here. Right? The chance of getting blue will be 2 over 4. Chance of getting red. Now you want red, that's the outcome. Then you just multiply the 3 over 5 times 2 over 4, and when you multiply them, you will get 3 over 10. 3 over 10. So the probability of RR is 3 over 10. So this will be 3 over 10.
So all is 2 red balls?
Yeah, 2 red balls, yes. Okay? Find the probability that you have a blue ball followed by a red ball. Find the probability of getting blue followed by red. Or blue then red. Yeah, so the word is important. I have to say something here. I have to say followed by, I have to say then. I have to show you the order is important. That the ball is the first ball is blue and the second is red. Okay? So that's how I use that. I use the word then, I always use blue then red. Will be the same result actually. It's 2 over 5 times 3 over 4, which will be actually also 3 over 10. Okay? Find the probability that you get exactly 1 blue. Exactly 1 blue ball. Exactly 1 blue ball. We're selecting 2. I'm selecting 2. And I'm saying exactly one of them is blue. That means what? That means the other must be red. Right? One is blue means the other must be red. So if one is blue and the other is red, do I care about the order here? No. I just want 1 blue. Could be the first, could be the second. This in fact means this is the probability that you got blue, red, or red, blue. So it doesn't matter which one you get.
So even in the one before, I don't see that the order...
No. This order is no. I said here between them. I said then. When I ask the question, I have to.
How does it matter? How does the order matter?
Select 1 ball. The first is blue and the second is red. It could be.
In the same case, after this, we're just multiplying.
Yeah. We here also multiplying, but here we're multiplying twice. Multiplying once for BR and another time for RB. And then I have 2 outcomes in this case, not just 1. When I don't care about the order, then I have another case, which is the blue first or the blue second. And the event now becomes larger.
Can we give second one make blue red or
Red, blue, yes.
make both?
Make both. Find the probability of both. And then, after you find the probability of both, we already have most of them, right? We already have the BR. The BR is actually what? We just 3 over 10, right? We got the BB also. The BB was 1 over 10, right? Okay, now missing what? Missing RB, which is also 3 over 10. So now I need both. So what do I do with both? Now I have each one is 3 over 10. What do I do? Add them, yes, because OR means union. So I add them. So the answer will be actually 3 over 10 plus 3 over 10, which is 6 over 10. So now we started looking at some of the questions require more than one outcome, and you need to have multiplication rule to calculate each outcome. And then, after you calculate each outcome probability, add them. Yes?
Yes, at least 1.
Very good question. This is actually was my next question. How did you know? I was going to say in the next question, at least 1. Let's do it again. Okay, I have 3 red balls because just became very busy. 2 blue. Another question is find the probability. Of course, we're selecting 2. Selecting 2. Find the probability that you got at least 1 red. Find the probability that you got at least 1 red. What does it mean at least 1 red? One or more. Very good. 1 or more. It's mean 1 red or 2 red. What is 1 red? RB or BR. And now 2 means RR. So that means I have 3 outcomes I have to get, and then I have to add their probabilities. Because or means union, which means I get them all together. Does it make sense? So at least one in this case means I have many outcomes. Okay, I deleted the tree diagram. I can just do it again quickly. BR, BR, BR. I need what? I need the BB, I need the BR, and I need the RB. Do I need the RR? Which one I need? The BB? No, I don't need this. I just need these three, right? Okay. Which was, each one of them was 3 over 10, remember? So all I have to do, the answer would be 3 over 10, 3 over 10, 3 over 10. That would give me 9 over 10. Okay? Does it make sense? That's what we did last time, right? We had 3 over 10, 3 over 10, 3 over 10. So when you add them, you get 9 over 10. So as you can see, there was a lot of questions I can ask from a tree diagram like this. Yes?
The question said at most one red, it's going to be BB and RB and
Yes, exactly. If you say at most one red, which means maximum 1 or 0, which could be the first and the second and the third, which will be 7 over 10. If I say at most one red, it will be 7 over 10. If we select 3 times, then the tree diagram will look like a bit more complicated, and it's very unlikely, but it might happen, in fact, if the question wants to be challenging. So you will have blue-red, you will have blue-red, right? And then you have also blue-red. But the problem is, you have only 2 blue. How many blues? 2 just, right? So you can't have blue again anymore. Khalas. That's it, not possible. In this case, you already have 2. So in this case, you only have red. For sure, it will be just red. There's no other option. And then you just have to fill the tree diagram and carefully check what is out. Okay, it's very unlikely. It might happen, but it will be like a challenging question. It's the same idea exactly. You want me to do it? Yeah? How many blue we said? 2? 2 over 5? 3 over 5? And this will be 1 over 4. And this will be 3 over 4. Here this will be 2 over 4, 2 over 4. Now if you take 1 over 4 blue, now there's no more blue. So it's only red. And you already, no, it's just 1. Just 1, because that's the only option. Right? It will be 3 over 3. 3 over 3, which is just 1. And you have blue, red. And then now when you reach here 3 over 4, how many? You took blue and red, so it will look like you have 3 red, right? You have 2 blue. So you took 1 blue and red. So how many? The chance of getting blue would be 1 over 3. In fact, 1 over 3. This would be 2 over 3. And this is again blue, red. Suppose that's it. Suppose the question: find the probability that you get a blue ball followed by 2 red balls. So in this case, you just multiply the blue times red, which are these probabilities, which will be 2 over 5 times 3 over 4 times 2 over 3. So that would be the case. Okay, when you simplify that, of course, this will go with this, so you just have 1 over 5. Okay? So that could be one of the, but it's very unlikely to have a question like that.
So you get the 1 of the
Which one? This?
No, 1.
Yeah, okay, that's 3 out of 3. You took a blue and then took a blue, so what remained? All red. So the chance you're getting selecting a ball, it has to be a red. Yeah, 3 out of 3. There's no other choices. Right? There's no other choice. Yeah, but this is complicated. Don't worry much about it. Let's just see something else more realistic. More realistic. I just have a simple branch. I gave you already a number of possible questions, which could be sometimes a little complicated, but it's possible. But in this case, I don't think it will be more than 2 stages. But I can have 3, 4, 5, 6, 7, 9, 10 stages, but the question has to be simple. Like all of them or none of them, like that. So if I have some of the questions like that, 20 women, 30 men, okay, this is a group in a company or something like that, and then you're selecting 5 people. You're selecting, okay, whatever, 7 people, anything. Find the probability that all of them are women. No. You always answer so quickly. Think one by one. The first guy selected, what's the chance it is women? 20 over 50. The second one selected will be women, 19 over 49 because it keeps reducing, right? And then keep reducing because every time you select 18 over 48 and then 17 over 47. How many of these? 7. It takes you a lot of time to do that, right? And then you multiply them when you add them. Multiply. This is a multiplication rule. This is a different, probabilities on the branch that give you the outcome. So that's 16 over, how many? 1, 2, 3, 4, 5. I need to have conservative for the space. So that's it. 46, 45, 44. And then I have to multiply all these 7 fractions to get the probability. Yes, that's the probability that all of them will make. We multiply to get one outcome. Any outcome. This is one outcome. This is, see, the tree diagram looks like this. Women or men, first one. And then women or men, so on. So you want one outcome at the end, which is women, 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 women here. That means all women. No, use this. You have a multiplication rule today. You have a multiplication rule today. So to get the outcome probability, which is www, how many? That's one outcome. After 7 selections, 7 steps. So to get one outcome, you multiply everything. You have a probability here, this number, this number, this number, this. You multiply all of it to get one outcome. If you need more than one outcome, each one of them will come from multiplication, and then you add them.
In this case, if we return back.
If you return back, which doesn't happen, then the probability will be always the same. Yes. Yes, yes. So exactly. So if you make this question with replacement, suppose I select and put it back, which doesn't happen for women and men, but it may happen for some other things. Okay, in this case, the probability will be always the same. So you have 20 over 50, 20 over 50, 20 over 50, always like that, 7 times. So it will be 20 over 50 power 7. That's the probability that you got 7 women. No, all of them women. The question will say with replacement. The question will say with replacement. Here the question must say that because it's just not usual.
The question is like the old question, the first one.
Yeah.
Like the dice and the coin. How can we tell if that's with replacement or without replacement?
It doesn't say anything, it's without replacement.
If it doesn't anything, it means yeah. But your question, when you talk about dice, this does not apply to dice. We're talking about multiple selection. Like we have a lot of things, and you're selecting from a lot of people, a lot of balls, a lot of transistors, a lot of anything, and you're selecting from them. That's just that only applies to the multiple selection example. The dice is something that repeat. That's different. And repeat exactly the same way. The coin repeat exactly the same way. Answering multiple choice question exactly randomly is exactly the same way. That's different. It doesn't have this option. Yeah.
The question asks all of them if you produce for all exams.
Unless if it say with replacement. If it say with replacement, don't reduce. You just keep the probability as they are. Okay.
This is just to know, right? Like you don't have to know with replacement.
Say it again.
This is just to know.
We will have example questions like this.
Yeah, some of the question will tell you we're selecting with replacement. Or every time you select something, you replace it back before you select again. If you tell you we replace it back before you're selecting again, it means everything go back to normal numbers, same numbers as original. So the numbers will not change every time, will be the same. So the question has to say that. All right, I think maybe you start doing the active learning before you get so tired. So just go to active learning 4C. Active learning 4C and try to solve the question. So the big variety of questions, I had to explain all of this. And then you have few of these in active learning 4C. Please go to active learning 4C.
The exam, you given the results or not yet?
Oh, not yet, not yet.